So here is our 7.5 homework. We're going to start out with number 15. So we're just going to describe how to obtain the graph of G from the graph F. So basically we're saying what change happened in G of X that was relative to its original kind of like parent function sort of thing. So when I'm looking at this and when I'm looking at this here, the only difference is that I have this plus 14 inside my root. So what this thing would have looked like if I were to do just a very quick high-level sketch is it would have started at 0 and going to go kind of up and to the right slowly like this. So when I look at this function, I'm saying, okay, well, what changed to give me this new one here? This plus 14 is really the opposite in what it appears to be. So my h value here is negative 14. So what this h value negative 14 means is it's going to go left 14. So this thing is now going to start all the way over here at negative 14 and then, kind of go up and do the same stuff. So in terms of what's happening here, it's going to shift left 14 units. Any questions on this one? Perfect. I'm just going to talk about a couple of these just so we can get like a little bit more of an understanding too in case people had other questions. In terms of for 16, the difference between these things, I've got this negative 10, which is going to make it go right 10. And then I've got this negative 3, which is going to make it go down, 3. So in terms of this one here, I have a negative sitting out in front, negative sitting out here. Okay, cool. This has a negative 10 on the outside. This does not. So this would be going down 10. And then last but not least here, I have no 6 and 5. So here I have 6 is going to go left 6, and this is going to go down 5. So just showing you a few different ones there.
I have a question.
Yeah.
For like the ones that are like number 15,
Mm-hmm.
just wondering how you would do this. If you were to have like a different like number like in front of like each of the like a different number, like if you had like 5 in front of like the like square root and then like 3 in front of a square root, how would you do that?
Yeah, so that one's the hardest to describe because it's basically just in a nutshell, I would just say it's stretched differently. So the thing is with the value out in front, the A value, it affects the stretch and it affects whether it opens up or down, or you can kind of think of it as a flip for the cube root stuff. So when I'm saying like whether it affects up or down, the thing we're talking about is the A value. So for the A value, if it's positive, we're going to say, okay, it's kind of just going to be normal. But if it's negative, it's going to be flipped from whatever normal is. So my original sort of square root function looks like that. The flipped version of that, where it's negative, would be going down like that. So if I were to talk about my cube root stuff, my normal cube root would look something like this, and that's with a positive A value. And so to have a negative A value, it would look something like that. Does that make sense? Just the positive and
Yeah.
negative part of it?
Yeah, that makes sense.
Okay. The next part is harder to draw. It's harder to explain, but it's the actual A factor. So I'm going to say we have our A, which is greater than 1. We have our absolute value of A, which is less than 1. And then we have our absolute value of A just equal 1. Well, this one is the parent function. This is pretty boring. This is like our normal. So in terms of what's happening with this one's going to happen faster. So I'm just going to try and draw, and again, try being the emphasis here, of let's say we had a value greater than 1, and it's going to be positive, and I'm going to say it's going to open up, something like that. So it's going to happen a little bit faster. The values are going to be a little bit higher in that regard. Does that make sense?
Yeah.
If it were negative, like say it was -2, it's still going to be happening faster. It's just that it would be happening faster, but going down negative. You know what I mean?
Yeah.
Perfect. So that's what that would look like. And then in terms of what the value less than 1 would look like, and again, this is absolute value of A, so I don't care whether it's positive or negative. I'm just focused on whether the thing is greater than or equal to, or excuse me, less than 1. So 1/2 versus -1/2 are two examples of this. So what this would actually look like is it would look like a more gradual version. So it'd be kind of like opening up like that. So still opening up, still happening the same, just slower. So 1/2 the values. So it'll take twice as long. Does that make sense?
Yeah.
Cool, perfect. Any other questions here? Solid. Let's look at 23. So here we're going to actually look at graphing. My graph is not going to be great, and that's okay. I guess I could copy in a blank coordinate plane so I can make it look semi-good. But here I just want to graph the function and state its domain and range. So when I'm looking at this, square root functions are the ones that have a domain restriction. If I had a cube root function, then I do not have a domain restriction. So these, again, have a domain and they have a range restriction on them. So when I look at this thing, I'm talking about the A, H, and K values. Well, here I don't see any H and I don't see any K. So my H and K here is 0. All right, cool, kind of boring, but whatever. And A value here of 1/3. So in terms of what's going on here, it's going to be opening up normal, all that stuff's the same. It's just that it's going to be kind of flattened out. So when I'm doing a problem like this, I would start out with my A, H, and K values, just so I explicitly know what they're going to be. A value here is a positive 1/3, H value is 0, K value is 0. So I'm going to start at the point HK. So when I'm plugging in this value, what I'm basically saying is 0 out whatever this thing is doing, and then this is going to be the vertical shift on that. So this is going to start at 0, 0. So that's going to be my first point. And when I do this, I'll set up a t-chart. Here's my x, here's my y. I'm going to start out at 0. Whoops. Oh no, the lag. Give it a sec here to catch up. There we go. So 0, 0 here. And now when I'm looking at this, I'm going to go out 1, and I'm going to go out 4. The reason I'm going out 1 and I'm going out 4 is because I want nice square roots. Again, if I wanted to go out 2, could I do it? Sure, but I'm going to get a messy square root. Here it's going to be slightly messy because we have a 1/3, but that's not an issue. So here when I plug in the value of 1, what happens? Well, I get 1/3 root 1. Root 1 is just 1, so this is going to be 1/3. Cool. Now I do it with 4. Now I have 1/3 root 4. Whoops, jumping ahead of myself here. The square root of 4 is 2, so here I have 1/3 times 2, which will give me 2/3. In terms of making a lackluster graph here, this thing would start at 0, 0. I'd go out here to 1 and 1/3. Pretty hard to represent, but there we go. And then I'd go out to 2 and 2/3. And then this thing is going to eventually be opening up, kind of looking like that. So this is what I'd be looking for in terms of steps and stuff on a test. So I'd be looking for these coordinate points, and I'd be looking for a graph that looks something like this. Again, this is like 1, 1, 2, you know, that sort of deal. Any questions on this one? Perfect. Now we'll do a cube root one. So, oh, actually, let's talk about domain and range here. Sorry. So let's talk about domain on this thing. For my domain, I am restricted by not being able to take the square root of a negative. Now again, square root, fourth root, sixth root, eighth root, any even root of a negative number is going to give me imaginary stuff. So I can't do that. So basically my domain is where x is good to go, okay? So where is going to be the range for this domain is going to come from where my root is going to be at least 0 or greater. So what I'm going to do is I'm going to set this thing, I'm going to say x is greater than or equal to 0. Well, that's, boom, done, just like that. Now, sometimes we'll have to do a little bit of work. So I'm just going to show you another example here. If I were looking at the domain here, I would set x plus 6 greater than or equal to 0, and then I would solve. So I would get an answer of x is greater than or equal to -6. Again, that's for number 26 here, but just showing you that my domain can be different. Does that make sense? Okay, so looking at here, that's my domain. All my x's greater than or equal to 0, and that's why we don't have any graph over here, right? There's nothing happening on this whole left part of the graph because I only have x's greater than or equal to 0. Now let's talk about the y's. So for my range, this is where, oops, y exists. Keep in mind that my x restrictions are going to affect my y restrictions. So here, I'm starting at 0, 0, and I'm opening up. Here's where I really want to pay attention to the a value. My a value here is positive. I don't care that it's 1/3. I mean, cool, it'll happen slower, but it's still positive. So it's still going to be opening up. So this thing started at 0 for my y's, and it's going to go up from there. So my y range is going to be y greater than or equal to 0. And this is going to be greater than or equal to my k value, right? If I had some k like a vertical shift here of 1/4, it would be greater than or equal to 1/4. Now, what would switch is if my a value was negative. So let's take a peek at this one here. So here my a value is negative, and I have a k value of -2. For this range, y is going to be less than or equal to -2. So again, here I am less than or equal to because my a value is negative. So opening below everything starting from, and then here's my highest point. If this were positive, it'd be y greater than or equal to -2. So now let's look at the same thing for 31. So here now we're looking at our cube root functions. So cube root functions here are a little bit easier. The reason that these are easier is our domain and range exists for all real numbers. So I can plug in any number, whether it be positive, negative, or 0, in for my x. So I'm just going to right out of the gate call my domain all real numbers. And then I'm going to say the same thing for my range. Here is going to be all real numbers. So now that I got that out of the way, let's look at what this graph would look like. This thing has an a value of 1/3, an h value of 0, and a k value of 0. Not really much going on here, but that's okay. So now as I look at this thing, I'm going to start out at hk, which for me is going to be 0, 0. Okay. From here, I'm going to very carefully pick these points. When I say very carefully, I'll explain what that means. So here are my x's, here's my y's. I'm going to start 0, 0 in the middle. Okay, I'm going to do two things. I'm going to go left 1, and I'm going to go left 8. The reason I'm going left 1 and left 8 is because I just want nice cube roots. -1 and -8 give me nice cube roots. I'm also going to go to the right 1 and to the right 8. So here I got 1 and 8. This is from where I start. So looking at this one, for example, this has a horizontal shift. Okay, this -5 means I'm going to go to the right 5. So I'd start at 5, and I'd go 1 to the right, and then 8 to the right, and I'd start at 5, and I'd go 1 to the left, 8 to the left. So these set of points are going to be different than these set. It's going to be this set of points is going to be different than this set. So now let's actually plug in some values and see what we get. So now I'm going to plug in my -8 here. If I plug in, -8, I'm going to be doing 1/2. Did I write down 1/3? I don't know where I wrote down 1/3. I meant to write down 1/2. That's my bad. Let me fix that real quick. There we go. So a value 1/2 here, cube root. So when I'm looking at this thing, I'm saying, okay, well, when I plug in my -8, let's see what happens. So I get 1/2 of my cube root. Whoops, 3s are hard. That's not a very good 3. We can do better than that. There we go. Of -8 here. So when I take the cube root of -8, I get a nice number, which is -2. So it's going to equal 1/2 times -2, which gives me -1. Cool. again, these values are maybe not as nice as other ones because it's 1/2 for my a value here, but that's okay. So now let's look at the next one. So the next one's going to be 1/2. Here I'm going to get cube root of here is -1. It's going to be 1/2 of -1 because the cube root of -1 is -1. And I get -1/2 here. I'm going to continue doing this for my other 2 points. I get +1/2 and a +1. So in terms of doing this graph at a very high level, this is what it looked like. I'm going to say this is um, 1 here, 1 here. I mean, this is hard to draw even remotely to scale, but whatever. I'm going to say I got 8 over here, -8 over here. There's -1. So first point was 0, 0. That's actually picking our color. So we get 0, 0. We said we have +1, and then it's going to be, or +1 and +1/2. So I'm going to try and represent this as like not quite all the way up. And then once we get to our 8, we had +1. Over here we had -1 and -1 and -1/2, and then I had -8, -1. So kind of tough for me to represent these accurately to scale, but that's okay. It looks like this thing that swoops up through and then continues on like that. Any questions on this one? Perfect. So for 47 here, we're looking at a right circular cone. It's got slant height of 1, so it's telling us this edge right here. We're told that the radius here is 1/2. The radius of this thing is given by r equals okay, so it's giving us 2 different. All right. So first thing to start out with is we have a right circular cone, or excuse me, a right circular cone, slant height 1, radius r, and it's telling us what r is here. So let's just do this. Here we got r is 1 over root pi times the square root of s plus pi over 4 minus 1/2, where S is the surface area of this thing. You want to graph this model and then find the surface area for this thing plugged in with 1 for R, or excuse me, 1 for slant height, and then 1/2 for our R value. So let's talk about graphing this thing. So really the only thing we care about here is that I want the which do we want to graph the model with? R is this thing. I mean, I guess it probably wants us to graph for our R value. Yeah, all right. We'll graph for R value. So basically what we're saying here is R is our Y and S is our X. So basically we can turn this into the stuff we've done previously just by making those little adjustments here. The stuff which is going to be happening here is that our A value is 1 over the square root of pi, which is like some messy fraction. I'm not sure what that is, so I'm going to do an approximation just so people can have an idea of like what it is that we're talking about. So 1, let's see here, 1 divided by the square root of pi gives me, we'll call it approximately 0.56. My h value here is going to be negative pi over 4. So call that negative 0.79. And so actually I should write what it actually equals. And then we'll do our approximation. I definitely wouldn't worry about needing to graph things like this. This is much more messy than you'd see on a test. So here's my h value equals this thing. So again, always offset the way that it looks. And then for my k value, it's going to actually equal -1/2. So this gives us an approximation of, approximately -0.79. Here we get approximately 0.56, and here for our k value, we get approximately 1/2. So in terms of what I would do here to graph this thing, I would start out with x's and y's. And so when I'm plugging this in, again, these are my r's here. These are my, whoops, I just swapped that around. S's here, my r's here. I'm going to take these values and plug them in. So the first one I'm going to start out is always going to be hk. So I'm going to start out with approximately -0.79. From here, I'm going to increase by 1. So I'm going to take that -0.79 and just add 1 to it. So I get 0.21. And then I'm going to add 4 to it. So I'm going to get 3.21. And then for my y values here, I'm going to start with whatever my k value was. So my k value here is -1/2. I'm going to just turn this into a decimal just because we're doing decimal approximations here. So I get -0.5 here, and then I want to take this number, plug it in, and see what I get. So when I plug this in, I'm going to be doing 2.1, and I'm going to be adding my pi over 4 here. So when I plug this value in, we'll get 1 to spit out. I don't want you guys to be like super hung up on like these particular values here because it doesn't really matter that much. But basically just imagine that I'm doing my 0.21 and I'm subtracting off, I'm adding the value here. So we get 0.21 plus 0.79. So inside here is 1. So here I now get root, or it should be 1 divided by root pi, which is our approximately 0.56 times 1, and then I'm subtracting 1/2. So this is going to give me approximately a value here is 0.56, so we get 0.06. So it's a little bit weird how this thing is changing, but basically every time we're going to be going up by 0.56 units. So I had the -0.5, I added my 0.56, and now it got me to 0.06. I'm going to do that again, add another 0.56 because I'm going up by what'll be a square root 2 here. So I'm going to end at 0.62. Again, these numbers are really ugly and whatever, but the concept is the same. So if I plugged in 3.21, 3.21 plus 0.79 is going to give me 4. Square root of 4 is 2. 2 times this thing is going to give me approximately, or 2 times this thing minus 1/2 is going to give me approximately 0.62. So again, just messy plugging in of numbers here, but nothing different than what we've been doing. So now in terms of the final graph, this thing would start out at -0.79. So again, I'm going to have a pretty hard time of actually graphing this remotely accurately, but that's okay. -0.79, -0.5, I don't know, something like that. From here, I'm going to go to 0.21 and then 0.06. So I don't know, somewhere like that. And then from here, I'm going to go to 3.21 and then call it 0.62. So somewhere like that. And this thing is opening up like that. So that's this problem in a nutshell. Again, would not worry about this. Very, very messy numbers. To find the surface area here for right circular cone by plugging this stuff in, 2 options. One is that we can just plug in the R value and then solve for the S, or we can solve for the S first and then plug in the R value. So I can show you guys that if you want me to, but again, I would not worry about it too much. Does anybody want to see that work done out?
Sure.
Sure. All right, let's do it. Oops. Just want this bit here. Maddie, the Chapter 7 test is posted, I think it is May 5th, Monday. Why is this not working for me here?
Do we have like all day to do it like last time?
Correct, same format.
Yay.
There we go. All right, so I have this formula here, and then it tells me slant height of 1, radius of 1/2. So I guess it's giving me S as slant height. No, it's giving us the surface area. So I don't know why it's even giving us. Whatever, we'll just plug in what we need. So we're given that 1/2 is the radius, so we'll plug it in. I'm gonna use, I already used red before, let's do blue down here. So looking at this thing, all I'm basically saying is now I have 1/2 equal to all this stuff. So again, this is just saying my radius is 1/2. And so I want to solve for my x value. So the first thing I'm going to do is I'm going to add 1/2 to both sides. So again, getting rid of my constant there. So now I'm saying I got 1 over square root pi times, I'm going to put this in a big set of parentheses, my root s plus pi over 4 equals 1 here. So from here now I'm going to, you can think of it two ways. One, you can multiply both sides by square root pi, or you can divide by 1 over square root pi. I personally think of it as multiplication. So I'm going to say multiply by square root pi over here, multiply by square root pi over here. So now on the left side, I'm left with my root s plus pi over 4. It's going to equal square root pi. From here, I'm going to square both sides. So square this, square that. I am left with s plus pi over 4 equals pi. I'm going to subtract off my pi over 4. And I'm left with my surface area is equal to 3/4 pi. So when we're looking at this thing, we could come up with an approximation if we wanted to. Let's see what we get. 3 pi over 4 gives us approximately, call it 2.36. So that would be the approximate surface area for this thing, or this would be the exact answer. Any questions here? Perfect, perfect. So one thing we could have also done is we could have just isolated the S first and then plugged in the R value afterwards. I just chose to plug it in first here. Doesn't really matter one way or the other.